Good morning, students. Sorry I can't be with you today. I am away at an AP Calculus conference, but the good news is that most of today's work is review. So the sub should have given you this packet that's titled 4.6 Graphs of Other Trig Functions. For today's notes, we're just going to focus on the tangent and the cotangent, and when I get back tomorrow, we will finish this packet and we will add in the pieces about graphing secant and cosecant. So we're just going to fill in the first page, and then you guys can take a break, work on the assignment that's listed at the end of that page, and then you can come back tomorrow to finish it up. So graphing tan and cotan, I know you've probably learned them before, but I always find that I forget what they look like because there's really just some memorization. So let's talk about what we know about the tangent function. When I am going to think about graphing a tangent function, I usually recall that tangent is the sine of my angle divided by the cosine of my angle. This helps me out because two of the values that I'm going to graph on my tangent function are going to be the zeros, which we like to do for a lot of different graphs, and also for this particular function, the asymptotes. So let's start thinking about the zeros first. When you have a function that is a quotient, the zeros come from the numerator. So if the sine of your angle is 0, then you know that you get a 0. You get a 0 of your tangent function. So we just want to ask ourselves, well, what angles do we know where the sine of theta is 0? And these are some very familiar ones, right? We would start at 0 and, oops, I got a little bit ahead of myself, of course. The next one would be pi and 2 pi and so on. And we could have gone in reverse counterclockwise, and we'll just make our dot, dot, dots. So if we think about what the graph of my tangent function should look like, the very first thing I might do is plot out my zeros. So we know we have one here. Let's make this one pi, and we'll just make it nice and easy so it fits. We'll go back to negative pi. The next thing I want to think about is, let me change colors just to keep it straight, is where my asymptotes would exist. So we cannot divide by 0. If the cosine of theta is 0, right, then the tangent has an undefined value or an asymptote. Well, where does this happen? You guys are very familiar now with the unit circle. This is going to happen when theta is pi over 2, 3 pi over 2, and so on, at all those odd multiples of pi over 2, or we could go backwards into the negative territory. So let's add in a few extra values here. We'll put our pi over 2, we'll put our 3 pi over 2, we'll throw in a negative pi over 2, and how about a negative 3 pi over 2? And at those values, I don't want to plot a point, I want to plot my asymptotes. My tangent function cannot cross, it cannot take those values. And the great thing about tan and cotan is that my threshold for you guys is much, much smaller in terms of what you need to graph. If we wanted to graph what's called the amplitude here, we could do that, and we could even connect it to the quarter points, because what's going to happen is that your quarter points, for example, at pi over 4, that's where you would hit your amplitude. So if this was a 1, I would have a point right here, and at negative pi over 4, you would be at negative 1. So you could include those points, and you could plot even more because we could compute the tan of pi over 6 and the tan of pi over 3 and so on and so on. But in general, my expectation for you guys for tan and cotan would be to graph the zeros, to graph the asymptotes, and then just to know the general shape. You do not need to plug in multiple values. You can make a note that the amplitude is equal to something, but you do not need to plot even the quarter points. So we're going to repeat this shape over here, something like that. And tangent is an increasing function. It goes uphill, and it's sort of on the left-hand side of each of those curves, it's going to fall towards negative infinity, and on the right-hand side of each curve, you're rising and rising to positive. So it looks like that. In fact, if you can find just the location of one of those things, what do you notice? Relate this back to our quarter point conversation for sine and cosine, right? If I think about each zero, the asymptote will always be halfway in between. So really, if I can find the period here, how far apart each zero is, then I can use half points, the halfway marker, to plot my asymptotes, and then I just need to sketch in that general shape. Over here, I just want to fill in a few things. Our general form looks exactly like it did for sine and cosine. The A, your amplitude, again, it will change sort of the curvature on each of these curves. The quarter point would show the amplitude, but I'm not asking you guys to actually graph A. The only really important thing would be that if A was negative, what would happen to these curves? Well, instead of tangent going up, tangent would go down. The B is going to change your period. So maybe we should jump ahead to that. Here for a tangent function, we should notice that they repeat every pi units. So the period of the tangent function is pi. And that is for the parent function. If b does not equal 1, if there is a horizontal stretch or shrink, then the period is equal to pi, the period for the parent function, divided by b. Note, this is a little different from sine and cosine, but if you remember it as the parent function's period divided by b, then it really is the same formula. It's just that the tangent function already has a shorter period. The C is our phase shift, and the D is going to move it up or down. So those values that I'm searching for that are zeros right now would actually be plotted on the D, y equals D axis. A couple other notes. The property, the domain, is all real numbers. Or maybe you wrote negative infinity to positive infinity. The range is actually the same thing. Oh, I just made a mistake. I was not looking closely. We have asymptotes, so it's all real numbers, except, and then what do we have to make our exceptions for? All those asymptotes, right? So n times pi over 2, where n is an odd integer. The zeros of that cosine function are going to be exceptions to my tangent function. And then again, this is an odd function. It has rotational symmetry about the origin, right? So again, I'm just gonna sketch this in. The period is the distance between any two asymptotes. The cotangent function graphs really similarly. And if you think about the steps that I just took to justify to you the tangent function, the cotangent just works in reverse. So let me scoot that up a little bit. Right? The cotangent function, if we go back to our formulas, is cosine over sine. It's the reciprocal of our tan function. So what's going to happen, right, is that our zeros are now going to come from our cosine function at negative pi over 2 and pi over 2 and 3 pi over 2. Everything that was an asymptote for the tan becomes a 0 for the cotan. And the sine function is what's going to determine our asymptotes, right? We'll have asymptotes, every time sine of theta equals 0. And so that's going to happen at 0 and pi and 2 pi and so on in both directions. Let me try to sketch it sort of right in line here, so we can really make a note of this, right? I plotted my pi over 2, I plotted my pi, I plotted 3 pi over 2, negative pi over 2, negative pi, negative 3 pi over 2. You guys really only need to graph 2 full periods, so 2 of the sort of squiggles. And I think I have an extra one here. So, right, our zeros are at the half markers. So here, here, here. And my asymptotes are at the whole numbers, whole multiples of pi, I should say. So at 0 and at pi. And I was trying to line them up so you could see the 0 became an asymptote, right? And the asymptote becomes the 0. So the cotangent function goes like this. And my curve, right, a tangent goes uphill, so you should remember or recall that cotangent, if I plotted more points, is going to go downhill. The exception to that would be if you had a negative multiplier in front of your cotan. Then it can become very difficult to see the difference. Again, the amplitude would show up as the value on pi over 4, or negative pi over 4 here. Or sorry, negative 3 pi over 4. It would be your quarter points. But I'm not asking you guys to graph those. It just becomes very difficult to plot too many points. The general form is the same as what we had above. So we have y equals a cotan bx minus c plus d. The domain, similar, right? It's all real numbers, except for the infinite number of exceptions. And this time, the asymptotes happened at those whole number multipliers of pi, except at n pi, where n is an integer. And the range, though, is all real numbers. There's no y value you could never take. This is also an odd function. It has rotational symmetry, and the period of cotangent is pi for the parent function. If your b is not equal to 1, if you have a multiplier inside of your cotangent function attached to that x, then you would take the original period of the parent and divide by b. Maybe I should put p equals. So we've made it through the parent functions, and I'll just go over a couple of quick examples with you. So here's an example, negative 3 times the tangent of 2x. Let's make a couple notes for ourselves, right? The negative is going to take our normal tangent function, and it's going to flip it upside down. So probably too many arrows here. The negative sign is going to make our general shape look actually more like a cotangent. Now, I asked you, or I told you on the front side, you don't, oops, sorry guys. You do not have to graph the amplitude, but the way that the directions are worded on your quiz or on your test are going to ask you to state it. So we would say that the amplitude is 3. You do not need to worry about including it in your graph. The other important point here, again, I know you couldn't see it because I was off the page, but it is reflected over the x-axis. And the last thing to deal with would be the 2x. The 2 on the inside means that my period, normally the period on a tangent function is pi. So this time I'm going to take and divide pi by 2. So my period is only pi over 2. Let's think about what we want to sketch. You just have to find one zero or one asymptote. If you can find one, then you can use the period and sort of the relationships to figure out the rest. So let's think about just graphing, instead of tan of 2x, sine of 2x over the cosine of 2x. With this one, let's assume we want to find the first 0. So my first 0, right, is going to happen when the sine of 2x is equal to 0. Well, forget the 2x for a moment. Where does that happen? Right? Sine is 0 for the first time, if you think about your unit circle, when my angle, 2x, is equal to 0. So it will happen when x is 0. The period is pi over 2, so I'm going to repeat that pattern over and over. That means that the next 0 should be exactly pi over 2 away. And the 0 after that would be another pi over 2, right? The distance between my zeros should be a period apart. But I also know that the asymptotes are going to fall halfway between those zeros. So I'm going to mark off the halfway point between 0 and pi over 2, and that would be pi over 4. Right? If I go halfway, I should have another asymptote at 3 pi over 4. And another one at 5 pi over 4. And that would give me enough space for 2 full cycles. If you went in the reverse, right, because I have plotted that 0 first, maybe you went into some negative territory, that's fine, then your asymptote would be at negative pi over 4. Now, the thing to remember is that it is a tan function, and I'm used to drawing tangents so that they increase, but that negative messed it up. So this one is actually going to look more like a cotangent function, and it will be decreasing. Again, that's because of the reflection. And so there's a pretty good sketch of my graph. We'll try a cotangent function next. Not a lot different, right? I would want to make a note that the amplitude is 2, but again, I'm not asking you guys to sketch in the amplitude. The period is going to be adjusted, right? Normal period for a cotan or tan function is pi, but there is a factor of a 1/3 here. And so that pi, instead of dividing by a third, I'm going to multiply by the reciprocal. So my period is 3 pi. So this one's pretty spread out. It's horizontally stretched because that factor of a third means I'm moving at a third of the pace. And I usually just try to find myself a starting point. On this one, with the cotangent functions, I like to start with the sine function because it's easy to find the first zero. The first zero of a sine function is always 0, no matter what your angle is inside, whether it's a 2x or an x/3. So on this one, rather than finding the first 0, I'm going to think about finding the first asymptote. Right? Because the first time that this would happen, that sine of x/3 is equal to 0, that would be when x/3 is 0 radians, or when x is 0. So I know that on my graph, right, at x is 0, I should have an asymptote. Now the scale matters because I don't want to draw this thing, as the same scale as I did on the last one. I'm just going to throw in the next asymptote, and I'll mark it accordingly, right? It should be 3 pi units away because it's a period away, right? Each asymptote would be separated by a period, just like in the above, I used that each 0 was separated by a period. And that would make over here, -3 pi would also have my asymptote. So here's my image so far, right? What am I missing? I need my 0. Halfway between 0 and 3 pi, right? 0 plus 3 pi is 3 pi, halfway over 2. So my zeros are going to happen at 3 pi over 2, and likewise, -3 pi over 2. It's a cotangent function. Cotangent normally is that decreasing shape. And again, I'm not going to worry about the amplitude so much. I'll just sketch it in. If we really needed an accurate graph, we could plot more points or use a graphing utility. And there you have it. Expectations are a little different. Use your period, find 1 0 or 1 asymptote, and sketch them in. Here's the assignment for tan and cotan. Solutions should be posted. I'll make sure I get them up for you guys so you can check your work. But get this done before tomorrow, because tomorrow we're going to finish these notes out, and I'll go over cosecant and secant in class together. Thanks for watching.